I wanted to start with, so we had 2 lab sections so far, the Monday and the Tuesday folks, and I wanted to go over just a couple of observations from those labs to help people out in today's section. The first thing that we noticed was if you're logging into the remote desktop connection through a PC as opposed to a Mac, it may be the case that your login credentials will be your full email address, netid@cornell.edu instead of just netid. So if you're trying to log in and it's saying incorrect credentials or something like that, try the full email address if you're logging in from a PC, and that'll probably fix it. The other thing we saw, and this is kind of mentioned in the lab write-up, but maybe not as explicitly as it should be, is when you are testing the audio through Zoom in the demo code. The demo code produces a pure tone, and Zoom is quite good at filtering out pure tones. So on the lab PC, when you join the Zoom call, if you open up the audio settings in Zoom and turn the background noise suppression as low as it'll go, the tone comes through quite nicely, or much more nicely than it would otherwise. And then you can change the frequency and hear it go up and down and stuff. The other odd bug that we were observing that I think we know the answer to is a situation where if a group is composed of student A and student B, we would see a situation where student A would log onto the PC, open up the programming environment, download software to the PIC, everything worked just fine, close out the remote desktop connection, and student B would log in, and MPLabX would say, yeah, I see the programmer there, but I can't connect to it. So we sometimes saw this error and we sometimes didn't see this error. And what the pattern seems to be is if student A doesn't close out everything before they log off with the remote desktop connection, then they're still running a process that debugger is attached to, and student B can't attach to it. So when you are finished with a working session, please just try to be disciplined about closing out all of your windows, close out the programming environment, and I think that'll solve the problem. If you forget during a lab section, it's not that big a deal. The solution is just I walk down the hallway and unplug it and plug it back in, and then everything works just fine. But just so that, you know, if you're working in some time of the day or night where I'm not on campus, it's nice to not have that problem. So just try to be disciplined about when you're done, close everything out. Basically as if you were leaving the lab in real life or in person, right? You'd want everything closed out.
If I could break in, it's also probably true that if nobody is around to reset it, you could probably reboot the lab machine and that will fix it. Probably.
Yeah, that probably will. Just make sure that you reboot and don't shut down. If you shut down the lab machine, then I have to go physically into the lab to turn it back on. You can reboot it. So if it's, you know, 10 p.m. and no one's on campus and you can't connect to the debugger, try rebooting the machine and that should solve the problem. It'll kick you out of the remote desktop session, but just give the machine a couple minutes to restart and then you should be able to reconnect, and that should solve the problem. I'll just remind people that this first week is a particularly large amount of reading. So I'm encouraging you to get started on that reading like now, essentially. And if you want to find the reading for lab 1, it's in the, above the lab assignments, there are recommended homework assignments for each lab that includes the reading for that lab and then some problems to work. So I'd recommend going through that reading and working through some of those problems before your lab section next week so that you can be the most efficient with your time that you can be. And then the last thing, most of you have already responded to this, but if you haven't, I put I embedded a Google form on the Canvas homepage. Cornell prefers that I get your permission to put lectures online, just in case it's just because it's possible that your voice or your name might pop up in a lecture. And since we're putting it somewhere public, it's good to get your permission to do that. So please just respond to that. And if you're not comfortable with that, that's totally fine. You can just indicate that on the Google form. And it's not so difficult for me to edit any identifying information out of the lectures. So just let me know and I'm happy to do that. But otherwise, I'll keep the lectures unlisted on YouTube until I get everyone's response, and then I'll make them public again. I do like to put them on YouTube just because experience shows that once they're time-stamped, they become way more usable. The way that the lectures get stored on Canvas, the feedback from the students is such that it's not super useful. because it's hard to search through topics. But once they're on YouTube, it's really easy to just skip through to whatever it is that you want to brush up on. Any questions about any administrative stuff before I get into content? Okay. So then what my plan for today, I'm going to share my screen, is in the first lab section, screen 1. In the first lab section, the whole exercise is to get some demo code up and running. And what I want to do for today and for Friday's lecture is really take our time and walk through that demo code. So I want to start this course basically with a comprehensive overview of the hardware that's available on the PIC and the software that we use to configure and control that hardware. So I'm going to start by just going through it generally and kind of waving my hands and pointing out some data sheets and stuff like that. But then I want to talk more specifically about hardware-software interaction by using that demo code as a case study. So we're going to walk through that basically as slowly as is required. But I want to be as thorough as I can with this. So let me start with a hardware-software overview, and interrupt me at any point. This class is, the central sort of theme of this class is hardware-software co-design. So it's about building projects that include both hardware and software, and that use hardware for the stuff that hardware is good at, and software for the stuff that software is good at, and for configuring and controlling that hardware. So we're going to go through some examples of the sorts of things that hardware is good at and the sorts of things that software is good at. But for many of you can likely think of some of these examples yourself. But I'm saying this because depending on your level of experience with microcontrollers, when I say hardware, you might be thinking only of sort of the sensors and devices and actuators and stuff that we plug into the I/O ports of something like a PIC32. And it certainly includes those things. But for the PIC32 and for many, many, many other microcontrollers, they come with a whole internal toolkit of hardware that is available for you to use in your designs. And in fact, in this class, you'll have to use those pieces of that hardware toolkit in your design to get the performance that's required to meet some of these lab objectives. So I want to go through exactly what that toolkit is. And then I'm going to go through the software libraries that we use to control that toolkit. So this is a diagram that is perhaps, there's too much on here to make it useful to look at in like 1 minute, but it's something that the hope is that people can go back and use this as a reference. But what I tried to do in this diagram is represent all of the hardware that's available in this device, all of the internal hardware tools that you can use, and the relationship between that hardware and the software libraries that we use to manipulate that hardware. So in the middle of this diagram in white, this is everything that's in that hardware toolkit. And we're going to talk through a lot of this stuff today, and then throughout the class, we'll get practice with most of these things. Not all of them. They're all obviously available for you to use in the final project if you would want. We won't get through all these things in all the labs. We'll get through a lot of them. So this is all the hardware that's available in the PIC32. And then the software library that we use to configure and control this hardware is something that's provided by Microchip. And it's this peripheral libraries for MPLAB C32 compiler, which is abbreviated to plib. So in all of our projects, we will include plib.c, which includes all of these all of these C libraries that allow for us to call functions that manipulate this hardware here in the middle. And we'll see some examples of this. So I wanted to start by just sort of giving an overview of some of the hardware that's available to you. Because some of this stuff, you look at it and it's sort of, you kind of expect for it to be there, sort of normal microcontroller stuff that you might expect to find in a microcontroller. Some of it's kind of surprising and kind of cool, and you might find some interesting uses for these things. So I'll just sort of start at the top. This is in no particular order. So each of these devices has 5 input capture modules. So an input capture module, I have a little slide just to show what this is. An input capture module is essentially just a register that has a timer for an input and uses some event for a load clock. So we have some register here. The value in that register is whatever this timer value is, and then it grabs that timer value at some event, the rising edge of some signal or something like this. What this is really useful for is very, very high precision timing. So if you want to very precisely measure the time from some start event to some terminating event, the input capture modules are really nice for that. This is in contrast to doing something like perhaps throwing an interrupt to grab a timer value, which for a lot of projects works really well. If you're doing like human speed stuff, that's wonderful. But keep in mind that it takes something like 70 cycles to get into an interrupt service routine. So if you care about cycle level timing, then you're going to be using these input capture modules. There are 5 of these available. And it's useful to talk about the utility of some of these hardware tools in combination with some others of these hardware tools. So these input capture modules, just to give a use case example for what this might be useful for, you can consider one of the other pieces of hardware that's available on these devices, which is each has a number of internal comparators. Comparator is a simple op-amp circuit that I'm sure many or all of you have seen, where we have our input into the positive pin of an op-amp, and then we hold the negative input of the op-amp to some reference voltage. And this is, you can configure this with plib as well, whatever this reference voltage is. And the idea is that whenever the input exceeds that reference voltage, the op-amp output snaps high. Whenever it's less, it snaps low. So what's really useful about these hardware tools is you can chain a lot of them. So you can have the output of one hardware device go to the input of some other hardware device so that you can build circuits that are useful for whatever application you're trying to achieve. So just as an example of this, you might consider chaining the internal comparator with the input capture module to do something like measure capacitance. And in fact, in previous semesters, this has been the first lab of this class, is to use these 2 pieces of hardware to do this. But the idea here is if you have some capacitor charging circuit that's going into the positive input of the internal comparator through an I/O port, and you have the output of that comparator going into the input capture module, then the idea is that you can start this timer and start charging this capacitor at the same time. And then when the value of, when the voltage on this capacitor exceeds the reference voltage, the output here would snap high, which would be your capture signal for the input capture module. And you could grab, with cycle level precision, you could grab the amount of time that it took for your capacitor to go from no voltage to some reference voltage. And with that knowledge and with some knowledge of capacitor charging curves, you could then do some math to calculate the capacitance, right? So, but this is very useful because a lot of the intelligence for this application is being offloaded to internal hardware tools. The only thing that software cycles are actually being expended to do here is configure this. Well, that's only done once though. And then we're actually expending software cycles to do the math that turns timer counts into a capacitance value. But everything else is done in hardware, which is really efficient. There are questions about this? Is it clear why these hardware tools are sort of useful? And you can be clever about how you chain these things. That's part of the exercise of a lot of these labs, is to think for a while about how you might cleverly chain some of these hardware tools to save yourself.
I had a question, Hunter.
CPU cycles. Yeah, go ahead.
What are the differences between software cycles and hardware cycles?
So by software cycles, I just mean, so we're running our CPU at like 40 megahertz, which means at 40 megahertz, you can have the CPU executing some instruction. And each time you ask the CPU to do each of those instructions that you put in software is a software cycle. And it's consuming some number of those cycles that you might use for some other task for the CPU to do. Hardware, I shouldn't be saying hardware cycles. If I'm saying that, that's kind of a slip of the that's just me being sloppy with language. It's just hardware. So we're configuring a circuit here that is an actual no kidding circuit. And then we're using the voltages in that circuit to do some math to figure out what capacitance is. So the idea is if you have 40 million CPU cycles to spend every second, by offloading a lot of this application to hardware, you're not spending any of those 40 million CPU cycles doing any of the stuff that hardware is doing. And what the hardware is doing in this case is charging the capacitor and then capturing the amount of time that it took for the capacitor to reach some reference voltage. Does that make sense?
Yeah, that makes sense.
Okay.
So it's triggered by the IO pin, not the timer then, right?
Yes, in this case, so the timer is the input to the register. So that's sort of the data that will get stored in that register is a timer value. And then it is told when to capture that value by, in this case, the output of the comparator, which is going in through an IO pin. The reason I have this going through an IO pin instead of directly in is just because on this architecture, it doesn't actually allow for you to map the output of the output compare directly to the input capture.
I see. So like we would be programming the IO pin to, I guess like any other time it just wouldn't meet threshold, right? So if the capacitor voltage wasn't high enough, then the output of the comparator would be like a logic level 0. So then it just wouldn't.
Exactly.
Okay, I see.
Exactly. So and the idea here is that this has two advantages. The first advantage is that by using that input capture module, you're getting the charge time of the capacitor in this example to cycle level precision. In contrast to doing something like throwing an interrupt to grab a timer value, which is not going to be, it's going to be quite precise compared to some other methods, but it's going to take you 70-ish cycles to get into that interrupt service routine. So it's precise to within 70 cycles, which is for some applications not that precise, right? With this, you are getting a very, very precise timing measurement. And then the other advantage, like I said, is you're doing all of this in hardware, which means you're freeing up some of those 40 million CPU cycles a second that you might otherwise have spent doing some of the logic associated with this circuit in software. That's now available to you. You can do other stuff with those CPU cycles. Any other questions? Okay. And all of this configuration of this hardware, right? So if we look at this picture, the configuration sorts of things that I'm talking about is this input to the comparator signal is getting mapped to a particular IO pin, right? And then the output of this comparator is getting mapped to some other IO pin. The input of this input capture is getting mapped to some IO pin. All of those sorts of configurations are done with that software library plib. We'll see some examples of this, but this essentially becomes a series of function or macro calls that configure. You tell the CPU, I want IO pin whatever to be attached to the positive input of the comparator. That becomes a particular line of setup code, which is a plib function call. You have a series of those that sets up this circuit in the way that you want, and then you run software associated with this circuit. Okay. So I'm just going to briefly talk through some of the other things some of the other hardware tools that are available for you to use in your designs. A lot of these act essentially as, well, I'll get to that in a moment. What I was going to say is they act as very simple coprocessors, which means a lot of these peripherals act as very, very simple processors that do very, very simple things completely separate from the main processor. So as an example, I'll just use the timer functions as an example. You have 5 timers available to you on this architecture. These timers act like really simple coprocessors that only know how to do a couple of things. They can count. They can compare outputs. So you can use these timers in combination with the output compare modules here to generate like pulse width modulation signals. And they can throw interrupts. But they can do all that stuff totally separately from the main CPU. So you can set up a timer to do those things, and you're not spending any of the 40 million CPU cycles a second to do the things that you've now asked this simple coprocessor to do. Each of those 5 timers are by default 16-bit timers. It turns out that some of them you can chain together to make 32-bit timers. So timers 2 and 3, you can chain together to make a 32-bit timer out of 2 16-bit timers. And the same is true of timers 4 and 5. You'll do that in Lab 4 to create a particularly long PWM signal for the servo motors. Not all these timers can be used interchangeably with all hardware. So timer 3, for example, can you can do some clever things here, and it takes reading of the data sheet to figure out exactly how all this stuff fits together. But just as an example, timer 3 can automatically trigger the analog to digital converter. So you could set up timer 3 to automatically trigger the analog to digital converter, and then you have some simple coprocessor that's just running a timer and gathering ADC samples completely separate from the main CPU. It's kind of useful, right? It's an efficient use of resources. And I'll mention too that timer 1 is being used by the threading program ProtoThreads that we use to architect all of our programs. So for that reason, timer 1 is not available for you in your designs because it's being used by the threading environment, but everything else is available for you to use, I believe. I mentioned output compare. I'll just mention that briefly because we're going to use this in Lab 4. There are 5 output compare channels. Each of these has the ability to compare the value of a selected timer with the value of 1 or 2 compare registers, depending on how you configure it. You can configure it to compare it to 1 compare register or 2 compare registers. And the idea here is that this is the timing diagram from the data sheet associated with the output compare module. So you can see some timer up here counting, and we have 2 compare modules. One has a value of 3000, another has a value of 3003. And every time the value of the timer matches either of these compare registers, it toggles the output of the output compare module. So you can see this is low. When there's a match between 3000 and 3000 in this output compare register, it toggles it to high. When there's another match between the other compare register, 3003 and 3003 for the timer value, it toggles it low again. So by playing with these 2 compare registers and by playing with the period of your timer, you can totally separately from the main CPU set up PWM signals, right? And you have 5 of these. So in principle, you could be driving 5 different servo motors with 5 different pulse width modulation signals and not be using any CPU cycles. Does that make sense? Okay. I'll mention just some of these other things. You have these boards have a direct memory access capability. So this is another very simple coprocessor. What this one does is, all that this little coprocessor is able to do is move data from one memory location to another memory location. So why might that be useful? Well, depending where, perhaps you want to move data from some memory location to the memory location associated with SPI data transfers, right? So we communicate with the DAC, for example, the digital to analog converter for sound synthesis, through an SPI channel. We're going to talk in detail about that SPI channel in a coming lecture, but in short, if you put data in the SPI transmit buffer, it will transmit that data through the SPI channel. So you could set up a DMA channel that takes some data that you have stored in memory and moves it to the SPI transfer buffer totally separately from the CPU and sends it out to the DAC so that you can have sounds being produced in response to events without using any CPU cycles. So say that in a previous lab, this was used for the video game lab in previous semesters, where there are a bunch of balls bouncing around a screen, and every time they hit a wall, you want to produce a sound effect. In order to do that quickly enough, you can't be interrupting into a sound synthesis interrupt service routine over and over and over again. You're going to spend all of your CPU cycles. So DMA is the way that we do this for that particular example. You can do other clever stuff with these DMA channels. So for example, I mentioned that timer 3 could trigger an analog to digital converter read. So you could do something like chain these hardware tools such that timer 3 does an automatic analog to digital converter read. So you're gathering data from the ADC and putting it to memory completely separately from the CPU, and then have the DMA channel move those ADC samples to somewhere else in memory. So you can be gathering analog to digital converter samples and moving them through memory, again, completely separately from the main CPU. And you can save all that CPU time to do whatever else you want to do. So this is what I mean by hardware-software co-design. It's about looking at the hardware that's available to you and thinking about how you can use this hardware together with software to build the best design that you can. And I'm sort of belaboring this point because this is true regardless of the fact that we're in a remote learning semester, right? All of this hardware design, you know, it's not whiteboard hardware. It's not burn your fingers on transistors hardware, but this is still hardware. And you think about it as hardware, and it goes into your design process, right? So this is still, the hardware software co-design is still very, very much a huge element of this course for this reason. It's because of this hardware toolkit that's available to you in the PIC32. Okay. And then just very briefly, I'll mention a few of these other things. We have a bunch of serializer, deserializer hardware peripherals. So there's SPI, there's I2C, there's UART. We'll talk through each of those in some more detail in some coming lectures. And then, of course, there's I/O ports, which are highly configurable. And I'm going to talk actually in more detail and sort of separately about these I/O ports, because these are actually quite configurable. And they're configurable through a tool called peripheral pin select, which just it deserves a little bit of separate consideration. So I'm going to talk about that separately. Okay. So what I want to do then is, with that sort of overview presented, I want to start to hopefully solidify some of these ideas by looking at some actual code. And the code that I want to look at is the example code that folks are running in lab this week. So let me download that. And by the way, I deliberately don't download this code beforehand. I'm doing this not because I want to waste your time, but because, as some of you have noticed, there's a huge amount of resources available on the course website. So when I go get something to use for class, I want you to see where I'm getting it, right? So in this case, I'm downloading the example software from the day 0 homework assignment, which is available here. So this is the software that you're going to be running. I'll open that up. So these are all the files that compose this project. As many of you have already worked through, there are header files and there are source files in here. And I want to talk through the main source file and then a few of these more important header files. I actually want to start in this config.h file. Just go over some of these configurations. All that this config.h file is doing is it sets clock rates, and it does a few other configurations. So if we just start at the top here and sort of go down, the first thing that happens here is, first of all, we suppress a few warnings, and then we include plib.h and we include standardIO.h. This isn't particularly interesting, except just to point out to you that this is where plib.h is getting included. So I talked about the fact that we're using this C library plib.h to do a lot of control of the hardware. And if you go to the main source file, you won't see plib.h included. You will see this config.h file included, and it's this config.h file that's including plib, just so that you know where this is coming from, right? So this is where plib gets included. And then we have a series of these configuration commands. This pound pragma is a compiler directive. It's just telling the compiler to do a few specific things. And in this particular case, for these first few lines, what we're telling the compiler to do is we're telling it how to configure the clock in the CPU. So it turns out that this CPU, its internal clock runs at 8 megahertz, but you can configure that internal clock through a phase locked loop to increase its speed. So instead of running at 8 megahertz, we'd like to run this. This is configuring it to run at 40 megahertz. Actually, you can turn this up to 60 megahertz, and I believe it's guaranteed up to 60. You can try to turn it up faster, and it might work, or it might not. But
it turns out, if I can interject, it turns out these CPUs are officially rated at 50. Everyone I've tried to overclock to 60 works, and everyone I've tried to overclock to 75 fails.
if you put it in ice water, maybe, you know, if we were in lab, it might be kind of fun to experiment with that. It would be a good final project, is to try to cool these things somehow and see how fast you could really get them going. But I'll talk through some of these lines. This first line, line 18, all that we're doing here is we are using we're configuring this to use the internal clock with the PLL option. So we're telling the compiler, we're going to use the internal clock, but we're going to put it through the phase locked loop in order to change the clock rate that the rest of the system uses. This particular phase locked loop, it has a clock divider on the input, and then it has a multiplier, and then it has a clock divider on the output. So we divide, multiply, and then divide again. It turns out that this particular PLL requires an input clock rate of 4 megahertz. So I mentioned that the internal clock rate is 8 megahertz. So we first divide the internal clock by 2 to drop it to 4 megahertz to input into the phase locked loop. We have an internal multiplier of 20. So that then cranks it up to 4 times 20, which is 80 megahertz. And then we divide the output by 2 to bring it down to 40 megahertz. Now, the obvious question is, why did you multiply by 20 instead of just multiplying by 10? It turns out multiply by 10 is just not an option. So multiply by 20 is an option. So we multiply by 20, divide by 2, and that gives us a 40 megahertz clock. We then separately set the IO bus frequency. So you can set the IO bus frequency to some other rate if you want to. We want this to also be 40 megahertz. So we just set the divisor to 1, which is just to say the bus frequency is the same as the clock frequency. And then these final 3 lines are just turning off a bunch of options that free up all of the IO ports for us to use. If you have various of these configurations enabled, they consume IO ports that are then unavailable for you to use in your project. And sometimes that's useful for what these things are, but in our case, we don't need these. So we just turn them off so that you can use any of the IO ports you want. We then just define a few variables so that we can use things like the system clock rate elsewhere. So we have this variable sysclock pound defined to 40 million, 40 megahertz. This number has to agree with the configurations that we've set up here. So if you are trying to speed up your CPU, just make sure that whatever you configure it to up here, make sure it agrees with what you have down here. because this appears elsewhere in the code. You want to make sure that you're doing it right. When might you want to speed up the CPU? Maybe the brave among you may want to do this in lab 2 for the Boyd's lab, the bird flocking lab. Part of your evaluation in that lab is how many birds can you simulate. And if you have a faster CPU, then you get more cycles between frame updates. So you could get a bigger flock. So some of you might try doing that.
Interject there that the library that was written for the TFT is not compliant with this value of sysclock, and you have to change the sysclock in the TFT driver also.
So I would make that your last optimization. We're getting a little ahead ourselves talking about lab 2, but I would optimize everything else. And then once you've got it working, if you want to try to turn up that clock rate and change the configurations, I would say that's the last thing to do, and then see what you can do it. I wouldn't do this first because you're opening a little bit of a can of worms, not a huge one, but one that you just might not want to open until the end of the lab. So we define a few variables that we use elsewhere, the sys clock and the bus clock rate. We pound define this use UART serial. We're just telling elsewhere in the code, and I can show you this either today or in the next lecture. By defining this, we're just telling the program that we plan to use serial communication, which in the pthreads header file causes it to set up some IO ports for UART communication with the lab PC. If you don't have this commented in, then it doesn't set up that UART interface, which if you're not using it is nice because it frees up those IO ports for you to use for other things. But because we're going to be communicating with every one of our labs through this Python interface run on the lab PC, which communicates through UART, in every one of our labs, we're going to want this commented in. Okay, so I just wouldn't touch this. And there's some other stuff that's commented out here. This use vref debug. I would also keep this commented out. Turns out you can use vref as a debugging tool for pthreads. It will change the voltage value on vref according to which thread is running. Just may be useful, but most of you will likely not want to mess with that. The final and important thing to note here is we're telling the system what baud rate we're going to be using through this UART serial interface. This baud rate must agree with the baud rate that you specify in the Python program that you run. Now in the demo code, they already agree. They're both configured to 115200. But if you mess with baud rate on either side, if you mess with the baud rate on the Python side, you need to make sure that you change your config.h file to make sure the baud rates agree, and vice versa. If you were to mess with it here for some reason, you want to make sure it agrees on the Python side. Are there any questions about this? So this is a file that you're going to want to check in every project just to make sure things like your baud rate agree. But unless you are doing some late stage optimizations like speeding up the clock or anything like that, you probably won't have to interact with this too much. Just pointing it out to show you what it does, to try to make it a little not mysterious, and to show you that this is where plib and some standard libraries are coming into the project. Okay. Any questions?
Yeah, can you please explain that part again where we divide by 2, then multiply by 20, and then divide by 2 again? Like, what's the need for that?
So all that we're doing here is the internal clock for the PIC32 by default runs at 8 megahertz. We would like for our clock rate to be faster. And this architecture allows for you to do that through a phase-locked loop. Phase-locked loop it's a hardware tool that allows for you to put some clock rate in and get a faster clock rate out, or a slower clock rate. But in this case, we're getting a faster clock rate out. This particular phase-locked loop has a clock divider on the input. It has an internal clock multiplier, and then it has a clock divider on the output. It requires that the input clock rate is 4 megahertz. So we have to divide the input by 2 to drop the internal 8 megahertz clock down to 4 megahertz. And then these remaining 2 are just whatever they need to be in order to get our desired output clock rate. In our case, our desired output clock rate is 40 megahertz. So we take that internal 4 megahertz clock, multiply it by 20, and then divide by 2, and we get 40 megahertz out. If you wanted this to be 60 megahertz, you would manipulate these two, the internal multiplier and the output divider, to try to get 60 here, or 50, or whatever you might want. You just have to read the data sheet to see what are the allowable multiplicative and dividing factors. Like I said, you can't multiply by 10, for example. So there's certain allowed multiplying values and certain allowed dividing values. And you choose whichever combination gives you the output that you want. In our case, we wanted 40 megahertz. Okay. I want to talk next about the main, the source file that contains main. So I'm going to open that up. Before I do, though, let me just go to, like I said, we structure all of our software using pthreads, which is a very lightweight threading library. And I want to just show you where you can go to read some more about this threading library. And maybe just talk at a very high level about it. So down here, if you go to ProtoThreads on PIC32, this is a whole web page about this threading environment. A lot of you likely have experience with writing threaded programs, but not all of you might. So let me just sort of briefly explain what's going on here. I think probably all of you have experience working with something like an Arduino, perhaps, where you'll recall that for sort of your standard Arduino code setup involves what they call the setup loop and then the loop, right? That you guys know what I'm talking about, where the idea is that setup runs once and then whatever you put in loop runs over and over and over and over again, right? So that some endless loop contained in that loop function call. What this threading environment allows for you to do is set up a bunch of different threads. Each of one is essentially a separate infinite while one loop. Just so in a single threaded program like on the Arduino, you have exactly one of those. For the sort of threaded program that we're writing, you'll have many of those. So there's different infinite while one loops. And what the scheduler does is switch from one to the other. So it allows for you to have different threads. Each of those threads is essentially a totally independent execution environment. And the scheduler will switch between those execution environments. Now, this is a non-preemptive threader. So what that means is a particular thread will hog the CPU and prevent any other thread from running until you tell it to yield. So it's up to you as the designer here to make all of these threads play nicely with one another. So if you're not careful and you have, say, 2 threads in your program and one starts running and you never have it yield, the other thread will never run. So it's up to you to decide when is each thread going to yield control of the CPU so that another thread can run. And you can do that flow control in a number of different ways, and many of those ways are described on this webpage. But you can have a particular thread yield until some event occurs. So that you would do that with something like a wait until, right? So perhaps at the top of your thread, you would have some PT wait until something, some logical value. And when that logical value asserts high, then that thread would become available to run. And your scheduler, every time when it next sees that thread, it would schedule it because that thread is now ready to run. You can have threads wait on semaphores so that they can signal among one another. You can have threads wait for a certain amount of time. So you could yield for a certain amount of milliseconds and then have it run again. But it's up to you to arrange things so that everything plays nicely together. This also becomes clear when you see it in action. But that's what we're up to here. Are there any questions about this? And by the way, I recognize that this is a lot of content quite quickly. This is one of those things where there are a lot of pieces to this project, and all of those pieces make the most sense when considered in relation to the other pieces, right? So the strategy that I'm taking in presenting this is to try to present all of it in a couple of days so that you can see how things relate to one another. But we are definitely going to go back through this a few times, right? So if this is a lot, that's okay, right? I recognize that this is a lot. It's not clear how to best to present this material except like this, to present all of it and the relationships, and then to revisit it frequently and to have you practice it. On the other side of this, another just very brief word of caution is some of you might have a lot of experience with this sort of software development. And I have had the repeated experience as a student of going to lectures about code and sitting in those lectures and going, that all makes sense, right? Like, I get it. It's no problem at all. And then I sit down to actually write something and I have no idea what I'm doing, right? This relates to, maybe some of you have heard of this thing called the Feynman effect. They used to say this about Richard Feynman, where you would go to his lecture and all of his students would say, yeah, that all makes total sense. And then they would go home and try to work a problem and have no idea what they were doing. Right? Just because he was such a gifted, that there is something about the nature of code that you can see it presented, it can make total sense. And then when you sit down, it doesn't make any sense at all. So this is just to encourage you that if you have lots of experience with this, and as I'm talking, you're thinking this is all very basic, please don't get lulled into a too false a sense of security. It's still a really good idea to start early, because when you sit down to actually start working on this, you're gonna discover things that maybe aren't so clear, and you wanna have time to ask questions about those things, okay? It's 9:53. I think I'm gonna save getting into the rest of the code for next time. This took a bit longer than I thought it would, but that's okay. Are there questions from anyone? So what I tried to present today was, this course is about hardware, software co-design. And I tried to make the point that despite the fact that we aren't this semester plugging hardware into the PIC32, there's a huge hardware library inside of the PIC32 that you still need to think about and that you still need to configure in your designs. So you are doing hardware, software co-design in this class, mostly using the internal tools in that PIC, and then also using the external devices that we've plugged in for you to interact with. So you have this whole library of hardware available to you. You configure that library with a C library from Microchip. And that C library is called plib. It is extremely well documented, and a lot of the reading for each lab is to read through the appropriate sections of the plib documentation. It's very well documented, but in all of your lab assignments, you will be doing function calls from plib to configure and control that hardware library. And then the last layer of abstraction here is we have the function calls from plib to actually configure and control that hardware. And then we are going to arrange our software using a threading package called ProtoThreads. And that too, it's documented on the website. We're going to spend more time in lecture going over it. But that is then how you arrange sort of your calls to plib. That makes sense? So there are a few levels of abstraction here. There's the hardware. The hardware is configured and controlled by a C library called plib. And then we arrange our whole all of our software using a threading environment called ProtoThreads. Like I said, we're going to spend the next few lectures talking through this in some more detail. Okay. So I'll see many of you in about an hour and a half, and I'll see the rest of you on Friday morning. Please start the reading for Lab 1. The first checkout for Lab 1 is not any like more technically challenging than any of the future checkouts, but because it's the first one, and because this is still sort of new and unfamiliar for folks, this is a particularly hard one, just because it's unfamiliar. So please do the reading and start preparing so that in next week's lab sections, we can be most efficient with our help for you. Okay, I will see all of you in a little bit then.
And Hunter, is it okay for people that are not in a given lab section to show up anyway if they want some help?
Yes, absolutely. And we were talking about this a little bit before the lab section, but it should be the case that every group will have their own dedicated lab PC. So that means that no other group in any other lab section will be using the same hardware that your group is using. So you can come to any lab section and your hardware will be available for you to use. And if you want to just come and ask questions, you're also obviously welcome to do that. But yes, absolutely. This was by design, right? We wanted it to be the case that everyone would have their own equipment so that they could come to any lab section, even the ones that you're not enrolled in, and get help if you want it.